Recall that we have recently used Strasson's algorithm for matrix multiplication to speed up the computation of transitive closure of graphs. But actually, we didn't need a matrix multiplication with arithmetic operations. We needed a so-called Boolean matrix multiplication, really. So the process that we have employed there was as follows. We took the modified matrix, adjacency matrix of graph G, and this matrix was just the standard adjacency matrix of graph G plus identity matrix of order n. And then we have squared that matrix, so we have computed AG hat times AG hat, and in the end we got a matrix where the ith entry corresponded to the number of paths of length at most 2. Then we have computed the square of this square, but actually we didn't really need the number of paths of length at most 2. We needed just to know whether the number of these paths is greater than 0 or is it 0. And so, instead of computing a number here, we'd better compute from the very beginning a 0 or 1 value. And to this problem corresponds the problem of Boolean matrix multiplication. So if we have two matrices, A and B, the Boolean product, which we'll denote like this, is equal to a matrix, which we'll call C, such that the ith position of this matrix, Cij, is equal not to the sum over all k of Aik times Bjk, but rather to a disjunction of conjunctions of Aik times Bkj. So we have conjunction here, but as these are 0 and 1 entries, conjunction is the same as multiplication. I will not place any different symbol here, but instead of the sum we have disjunction. Or mathematically, if we like some numeric operation, this would be taking maximum of these values. So now, if we plug the modified adjacency matrix as A and B into this definition of Boolean product, indeed we see that the Ij entry in the Boolean product of Ag hat by Ag hat will be equal to 1 if at least one of products like this will be equal to 1. So indeed, instead of the number of paths, we'll see existence of paths. So how can we compute a Boolean product of two matrices, not relying on Strasson's algorithm, and not treating these numbers as just integers, and then getting back all positive entries of the result to ones? This is the question that we'll now work on. So for computing Boolean products of two n by m matrices, Strasson's algorithm tells us that we can do it in time big O of n to the power of log 27. That's roughly n to the power of 2.81. And we have improvements here, of course, so we know that matrix multiplication can be carried out in time big O of n to the power 2.38, but these algorithms that actually perform the multiplication with this theoretic time complexity are galactic algorithms. Galactic algorithms is an informal term which is coined to name algorithms that have good theoretical complexity, but in practice the constant in this big O absolutely invalidates any practical use of the algorithm. So Strasson's algorithm can actually be used for reasonably large matrices, and this algorithm is used extensively in practice, whereas these algorithms are never used, at least for now, until it hasn't been figured out how to reduce these constants in big O to something reasonable. And in this way, sometimes the algorithm that has worse theoretical complexity can outperform the algorithm that has better theoretical complexity. So we'll now learn an algorithm that has worse theoretical complexity than Strasson's, but in some cases it may actually outperform Strasson's algorithm, and the general technique which is used in the current algorithm is useful, and it can be applied to many different problems for getting a logarithmic speedup. The runtime of our algorithm would be just big O of n cubed over logarithm of n. So we get just a logarithmic improvement factor over school book multiplication of matrices. But still, in many cases, this scheme can be more practical even than this one, and also the general ideas can be used in many other contexts. So this is why we study this algorithm now. This algorithm is called the algorithm of 4 Russians, just because the corresponding article was published by 4 Russian authors. And it has this standard name in the algorithmic literature. So suppose that we need to compute the matrix of this kind, and to do so, we'll split our matrices A and B into blocks. So the matrix A will split into these kind of blocks, and the matrix B will split into these kind of blocks. And the size of the blocks here would be logarithmic of n. So here we have log n and log n. Here we'll assume that n is divisible by log n, just not to mess with floor and ceiling functions here. But this technique easily translates to the case when n is not divisible by log n. So thus we can denote these stripes as a1 through a sub n over log n, and b1 through b n over log n. And we now see that when we're computing the element of C standing in some row and in some column, we're taking, as always, the corresponding row of A, the corresponding column of B, and the elements that we have here, they interact with the elements that are here, and so on. So the standard analysis of what we have with block matrices allows us to write that the matrix C actually can be expressed as disjunction for k from 1 to the number of blocks, and here we are multiplying a k in a Boolean way by b k. So actually this would work even for non-Boolean multiplication or for standard multiplication of matrices, but now we are considering the Boolean one. So what we'll now do, we'll think on how to compute each of these Boolean products in time big O of n squared. And thus, in the end, we'll get complexity of n squared multiplied by n over log n, which will give us the complexity of big O of n cubed over log n.